Hello everyone, welcome to this tutorial on E3SM Diagnostics Package, E3SM Diax version 2. My name is Jill, I'm from Lawrence Livermore National Lab. In this tutorial, I will first briefly introduce the package and then walk you through the steps to run the package. E3SM Diax is a modernly designed Python-based diagnostics package being actively developed for supporting E3SM model development. The primary goal is to bring analysis and datasets identified by E3SM scientists quickly into routine evaluation workflow to facilitate model development. Initially, the evaluation sets were modeled after NCAR's Atmosphere Diagnostics Package AMWG. Most important sets were implemented in E3SM Diax during version 1 development. The package has a number of features I'd like to highlight. It is flexible to add new observational datasets, diagnostics, and to modify aspects of the figures. It's a Conda package. The installation, configuration, and execution steps are straightforward. The program runs fast with multiprocessing. Lastly, provenance of runs is saved to allow for reproducing diagnostics figures. We aim to stay up to date with observational datasets, so that newer editions of OBS are being used in our evaluation. The package is developed for supporting E3SM with the consideration of accommodating CMIP-style model data. Therefore, it can be used as a community tool. This slide shows current diagnostic sets available. The first milestone of E3SM Diax was to complete the key basic sets as those from AMWG package. As shown on the left side, we have implemented lat-long map accompanying with tables and Taylor diagrams summarizing metrics from the lat-long maps, pressure versus zonal mean and pressure versus meridional mean plots, polar maps, zonal mean line plot, and cusp joint histograms. Each 3-panel plots often composed of test data, reference data, and the difference. The reference data could be observation or another model run. Either pre-calculated climatology files or monthly time series can be used as input of these sets. Moving on to version 2, on the right-hand side, we now have support for annual mean time series analysis, ENSO Diax, and QBO Diax. These new sets take only monthly time series as input. For input data requirements, unlike NPACE analysis for ocean component, E3SM Diax only takes data on regular lat-long grids. Therefore, one has to process the raw E3SM atmospheric model output into the climatology and time series files. Using NCO, the NCO instructions can be found in the link provided here. Note that each set of climo and time series files needs to be put in different directories. Here are some example file names following required naming patterns for climo and time series files, respectively. Most users often only look at basic sets of Diax. In this case, having seasonal climatology data ready is sufficient. For first-time users, we recommend you to download the example data from our data server from the provided link. For installation, for E3SM groups who have access to E3SM supported machines, E3SM Diax is pre-installed through E3SM Unified, which is a Conda environment pulls together Python and other E3SM analysis tools. To activate this conda environment, one can simply source a bash script available on each machine. In addition, observational and example data for testing are also available on these machines. For users want to run on other Linux or Mac OS machines, or would like to install latest version of E3SM Diagnostics that is not yet supported within E3SM Unified, here is the instructions. First step is to install Miniconda and to initiate the Conda environment. If you haven't installed Anaconda, Miniconda is a light version of Anaconda and only include Python and some basic packages. Therefore, it takes smaller space and is faster to install. There are two ways to create the E3SM Diagnostics. Firstly is to create the environment through an environment YAML files. In the YAML file, all the versions of each dependencies are pinned down. This way, the installation process is faster because Conda doesn't need to decide which version to pick up. The downside is that if any pinned down version of packages are broken on Conda channels, this installation method would fail. Alternatively, one can just create an environment from the E3SM Diagnostics build released to E3SM's Anaconda channel. The example command line here used version 2.1.1, which is the latest tag as I'm making this video. You should bump up the version number with latest E3SM Diagnostics release. Once the new environment is created, activate the environment with conda activate. Again, to set up E3SM Diagnostics on the new machine, you need to download the observational datasets and example data files for testing. For basic Diagnostics sets, you only need the climatology folder, which is much smaller in size than time series folder. Now I want to show the configuration process. In version 2 of the package, we introduced a new way to run with a clear interface to pass in parameters. Although V1 configuration is still compatible, to run the newly added sets, the new interface is required. On this slide, it shows the example run script to pass in parameters for a basic setup using pre-computed climatology files. In the Python script, all required parameters are set up through the param object. The required parameters include data path for reference data, data path for test data, and test data name, which often is the case name of the E3SM simulation. Selected seasons, the result directory to save output, including the HTML files. Here I use a path on Corey, where the HTML pages can be hosted online to share with others. Multiprocessing and the num of workers are set for parallelized the run. Without setting these two, the run will be in serial. In terms of timing, on Corey Haswell, with 32 processes on one node, this config takes about 3.5 minutes. Some useful parameters are listed here but commented out for this configuration. By default, the test name is being printed as the title of plots. The short test name is useful when the test name is too long or a different name for plots is desired. The run type needs to be set for model versus model run. The default is model versus ops. Title for difference plot can be renamed using diff title. The output figure format can be specified to be PNG, PDF, or SVG. If output format subplot is specified, the subplot of 3-panel plots can be saved individually. When save netcdf parameter is set to true, the data being plotted is saved as a netcdf file for potential reproduction of figures. At the end of the script is to specify the sets to be run. You can pick and choose from any of these listed sets. In this script, we are running all the basic sets. Last line is to pass in the parameters in E3SM Diagnostics runner. The next run script is for all sets configuration. This one includes both the basic set and the newly added sets that use monthly time series as input. Compared to the last configuration, here we need to define additional parameter objects for individual new diag sets. The setting for core parameter is the same as with the basic configuration. For each of the new set, the data passes are changed to use the directories with time series files, and the start year and end year need to be set up for selecting the time segments from the time series files. In this example, we use the same time periods for each analysis, but you are able to use different time segments for each. Lastly, the new sets are specified in sets to run, and the additional parameter objects are passed in E3SM Diagnostics runner. By looking at this run script, we can see that allowing each new analysis to have their own individual parameter space offers large flexibility to introduce new diagnostics. Again, with 32 processors on one Haswell node on Cori, the wall time is about 15 minutes. Okay, let's practice running this configuration on Cori NERSC. I'm going to quit slideshow and open up a terminal window. Here is a terminal window that I already logged into Cori. Let's make a new directory for the tutorial example. And let's download the tutorial example from our GitHub repo. Now it's here, and only slight modification is needed in order to run. This script is exactly the same as what I was shown earlier. In this case, the only thing needed to be added is the results directory. You should replace this directory with something that you have written permission with. In my case, I'm going to change the folder name into Demo 2020 and save and quit. Now we are ready to actually running. Now we are ready to actually run the script. So it is not recommended to run multi-processing program on the login node. Let's first request an interactive session with one single node from Haswell. Here I use debug partition. It allows maximum times of 30 minutes. Usually it takes much faster to get a node than a regular partition. Okay, the node is ready for job. I will need to activate my pre-installed E3SM Diagnostics environment. Okay. And lastly, to issue the run command, Python As I said, the whole process will take about 15 minutes. While the program is running on the background, I'm going to walk you through the output viewer I pre-made. Here is the output viewer of E3SM Diagnostics running the run script. On the top, you can see the version of the package, and the test data set is E3SM v1. In this case, we are running a model versus ops config. Therefore, the reference data is observation and reanalysis. The diagnostics results are grouped by sets. And at the bottom, there is a provenance link. Here we saved the command used to run this script and the environment YAML file and the tutorial example. So this is most useful when you get an E3SM Diagnostics viewer from someone else and you want to check out where the data is and if you want to reproduce the diagnostics run. So let's check out some output figures. This is the main page hosts the latitude longitude contour maps. The variables are grouped by observational datasets. And here is a drop-down menu that you can jump to different observational datasets. We can go into ERA Intron and look at all the variables comparing the model to ERA Intron data. Let's look at the global precipitation. And 2 seasons are selected for this configuration. This is for the annual mean. This is a 3-panel plot for model data, reference data, and the difference. What I want to highlight is the use for the metadata at the bottom. Here it shows a single command to recreate this image. To only recreate this single image, you can type in this whole command line in your terminal window. And if you want to slightly tweak, for example, the contour levels, or you want to change to a different color map, you can feel free to do so. And the result directory needs to be changed to somewhere else so that the original output viewer is not interrupted. And you can use this arrow to go to the JJA mean. Let's go back to the main viewer. Okay, and now next I want to show some results from the newly added diagnostics. Let's start with ENSO. The ENSO diagnostics composed of 2 components. The first one is the maps on regression coefficient of atmospheric fields over SST anomaly. Again, we shows model versus ops, and it's a difference map. The second component of Untitled Diax is the scatter plot of atmospheric feedback on SST anomalies. This is an example of surface latent heat fluxes anomaly versus surface temperature anomaly over Nino 3 region. For QBO diagnostics, we include a 3-panel plot. They are QBO index, amplitude, and power spectral density of zonal wind. And lastly is the area mean time series. This set gives the annual mean time series over multiple regions for multiple variables. Okay, that's what I want to talk about using the viewer.